Welcome to Seismic Sound Off, exploring the depth and usefulness of geophysics for the scientific community and the public. I'm your host, Andrew Geary. In this episode, Fabien Allo highlights his award-winning article, Characterization of a Carbonate Geothermal Reservoir using Rock Physics-Guided Deep Neural Networks. Fabien shares the potential of deep neural networks in integrating seismic data for reservoir characterization. He explains why deep neural networks have yet to be widely utilized in the energy industry and why utilizing a training set was key to this study. Fabien also details why they did not include any original wells in the final training set and the advantages of neural networks over seismic inversion. He closes with how this method of training neural networks on synthetic data might be useful beyond the application to a geothermal study. This episode is an exciting opportunity to hear directly from an award-winning author on some of today's most cutting-edge geophysics tools. To read this award-winning paper and find Fabien's complete biography, visit seg.org/podcast or check out the episode show notes where you're listening. And now, my conversation with Fabien Allo. And before going in depth on this paper, could you give a short summary of the results of this study?
Yeah, sure. The objective of the study was really to characterize the porosity of carbonate rocks from the Dogger Formation in the Paris Basin to help guide the location and design of future geothermal wells in the area. And this was really a first-of-a-kind pilot project. We wanted to evaluate whether sufficient subsurface information could be extracted from legacy well and seismic data. As you may know, budget constraints usually prevent acquisition of new state-of-the-art data for energy transition projects. In terms of the main task of this commercial project was really to run a conventional post-stack seismic inversion on various 2D lines. But we took the advantage of this opportunity to compare it with machine learning techniques that we've been looking at for quite a while as a side R&D project. And we were actually surprised to see that deep neural networks gave similar, if not better, results in terms of formation porosity. And I also consider the workflow to be quicker and simpler than a conventional seismic inversion for a standard user.
Yeah, when you think of machine learning, you definitely one of the benefits you think is it moving quicker. And you mentioned deep neural networks there. What potential do you see deep neural networks have in integrating seismic data for reservoir characterization?
I can see two potential things happening. I really believe that the deep neural networks can make the seismic reservoir characterization more accessible to a wider range of users by making the process more user-friendly and more straightforward. And I also see a clear advantage in an exploration setting with little to no well control compared to conventional seismic inversion.
Why do you think deep neural networks have yet to be widely utilized in the energy industry?
Well, that's a good question. And I can see two main reasons on my side. I think compared to other disciplines like image recognition, there's a lack of training data, well-logged data in our case, to train those neural networks. And even if there is sufficient training data available, usually you'll find out that it's biased. The logging tools are often restricted to the target zone, where the rock is the most porous and the most permeable.
Yeah, speaking of training set, you did utilize one in this study. Why was creating and using this training set a key part of this paper?
To me, that was the really exciting part of that project. We already knew by experience that neural network could be trained on synthetic data, which does remove those two limitations we just discussed. But the challenge here was to come up with a workflow to generate realistic pseudo-wells to train the neural network with. I think we found a good solution, but I would say we need to use due care and attention when we create synthetic data. They need to be representative of the field, of the formation you're working on. To me, there is a clear danger of bias as well if you only take favorable geological scenario in consideration when you build that synthetic data.
Yeah, and one of the things that, this is a real world project and you're working in the Dogger Formation for this. How did the data or lack of data from the wells impact the methods used to characterize the formation better?
Yeah, as I said before, so the main task of that commercial project was really to run a conventional seismic inversion. But here, the lack of well control made it very challenging, and I guess the results were questionable. So that's why we were looking at alternative approaches, such as the neural networks that can make use of synthetic data.
Yeah, and speaking of synthetic data, how did you go about simulating a set of these realistic pseudo wells?
Yeah, I guess that's the art of the paper itself, and here we've relied on our knowledge of data analysis at CGG. So if I go through the workflow very quickly, we use the existing wells as a base scenario from which we extracted the main trends from the petrophysical properties of interest. So in our case was porosity and volume of clay. And those main trends really represent the backbone of the pseudologs. And then subsequently, we modify them per geological formation based on a set of alternative scenarios. Like, for example, what if I make the reservoir properties better or worse? Or what if I make the reservoir intervals thicker or thinner? And the second part is the addition of some high frequency variations, which are based on the vertical variability that we observe on the original well log data. So I guess at the end, whether the petrophysical pseudologs are realistic or not is going to depend on the extent of the modifications of the background trend you make and the amount of added high frequency variations.
Kind of build on that. How did you approach deriving these elastic pseudo logs?
Yeah, so that's really kind of the second part of the workflow. So in that first part, you would simulate some alternative petrophysical logs, and then to arrive to the elastic pseudologs, we use some rock physics models that act as a translator between the petrophysical properties and the elastic attributes. So those models were calibrated on the original well data, where we knew both the petrophysicals and the elastic properties. And we just applied those calibrated rock physics models to the simulated petrophysical pseudologs.
Yeah, one of the interesting things, though, there were wells at this formation, original wells, but at the end of the day, you didn't include any of them in the training set. Why did you remove those original wells for the final training set?
Yeah, I guess that's always kind of a talking point, whether you should include or not your original data in the neural network. In this case, we decided not to include them, just to keep them as test wells to evaluate the performance of the neural networks. That allows us to evaluate some of the limitations that I listed in the papers. I would say that in that case, the pseudologs we created were pretty close to the original logs, so I'm not sure it would make a huge difference whether you would include them or not in that particular case.
Kind of nice to have something to check your work, essentially. That is a nice aspect of that. One of the things that are in there, you have these deep feed forward neural networks, a little hard to say there. Regarding those, why is this distinction between rock physics guided and rock physics driven important?
I'm not sure whether it's important or not, but what I wanted to make the distinction between here is the neural networks that are merely trained on data generated through rock physics models, like we did in this study, and neural networks with actual embedded rock physics rules or equations. It's kind of unclear to me at the moment whether one type is better than the other. To me, there are just two different ways of integrating rock physics constraints within the neural networks. That maybe I would expect the second type might be able to extrapolate better beyond the cases encountered in the training data. But again, yeah, it remains to be proven.
What are some of the advantages or potential advantages of neural networks over seismic inversion?
First, as I mentioned before, I believe that neural network can be more user-friendly in their application, so open their application to a wider range of users. So they've got the potential to streamline the inversion process by directly estimating the reservoir properties of interest from seismic amplitudes. Something that we can already do with techniques like petrophysical seismic inversion. It's possible, but usually it's kind of limited to expert users. Here, the neural network would open it to a wider range of users. Also, we've already mentioned that unlike seismic inversion, the neural network can make use of synthetic data, and that can make a big difference in, for example, in exploration setting. If you've got no well at all, you can't even run a seismic inversion, so you're left with a neural network only. I can think also at analogs. So neural networks, you can rely on analogs. For example, if you were to train a neural network to characterize a formation offshore Brazil, then you could apply the exact same neural network without having to retrain it at all on an analog formation on the other side of the Atlantic, offshore West Africa. That's great for that. And maybe another practical aspect as well is I think neural networks are quicker to apply than conventional inversion. It might be a bit time consuming to train them, but once they're trained, the application is very, very fast. So on the practical aspect, it can make a difference in terms of cost.
Have any of the limitations or pitfalls you note in this paper been reduced since the publication of it?
Not really, unfortunately. I haven't had much time to work on those. But what I would say is that dependency on a good quality low-frequency model might still be an issue. But as broadband seismic data is becoming increasingly accessible, I expect that issue will disappear in the medium term. What I'm more concerned about is the scaling of the input data that's given to the neural network. It does have a big impact on the results, and it can be difficult to calibrate properly when you've got a limited number of wells in your project. And we've also discussed already about the representativity of the synthetic training set and the dangers that lurk there. So I'm quite excited about our ongoing effort towards a tighter integration with geological modeling.
Beyond this application to a geothermal study, where else might this method of training neural networks on synthetic data be useful?
Almost anything, any application you could think of that can make use of extra synthetic data, I would say. If we stay in the energy sector, it's becoming really common use in the oil and gas exploration. If you look at the energy transition context, I can see it being used for screening of potential geological CO2 storage sites. But really your ideas are the limit, really.
That's pretty exciting. What would be your punchline as we are closing out this conversation?
Well, based on this particular study, I would say never underestimate the value of legacy data. Things are evolving very quickly. Data transformation, seismic imaging, machine learning technologies, all of that has come a long way in the past few decades. And really, it's giving new possibilities to do more with existing data. I think it's great news for the energy transition business.
I like that energy transition business. I like that phrase. And lastly here, what principal teaching or point of view has helped you succeed in your field?
Well, it's difficult to pinpoint just the one, so maybe I'll give a few of them. And they actually all apply to that particular study. So first, I would say, take every opportunity that comes your way to try new things. So in that case, that particular application of neural networks was not at all part of the initial project. It was kind of a side project. And it just ended up being a great project at the end. Without taking that opportunity, there wouldn't have been a best paper in the leading edge at all. Second, be persistent. It never really works as intended the first time. In that case, the initial results were not that great, but we kept going at it, and at the end, we managed to get something that worked quite well. Maybe another one is keep questioning yourself and others. Don't take any results as granted. Just make sure that it makes sense. In that case, as I said, the first results were really questionable as well. So we had to go back and back and back until it made sense. And maybe the last one would be strive to learn something new every day. In that particular project, we learned a lot along the way.
Well, I appreciate you highlighting this paper. Congratulations on the honor, and thanks for talking a little bit more about it in depth today.
Yeah, no, thank you very much for the opportunity to talk about it.
You reached the end of Seismic Sound Off. Thank you for listening to this episode. If you want to be the first to know about the next episode, please follow or subscribe to the podcast wherever you listen to podcasts. Two of my favorites are Apple Podcasts and Spotify. If you have episode ideas, feedback for the show, or want to sponsor a future episode, visit seg.org/podcast and find the box titled Contact Seismic Sound Off. Zach Bridges created original music for this show. This episode was hosted, edited, and produced by me, Andrew Geary at Treasurement. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.